Before I get started, I just wanted to acknowledge that we're gathered here tonight on the traditional lands of the Haudenosaunee and Anishinaabe peoples. I'm really fortunate for the opportunity to gather here and learn and talk about astronomy, and really thankful to have you all here to do that with. Tonight we have a really great talk by our very own Lawrence Widrow. Larry's been a professor here at Queen's since 1993. Before that, he did his PhD at the University of Chicago, as well as a postdoc at the Harvard-Smithsonian Center for Astrophysics and the Canadian Institute for Theoretical Astrophysics. Larry's research is primarily focused around theoretical astrophysics, currently working on looking at the interactions of the stellar disks of galaxies, especially the Milky Way. Tonight is a really great talk, in keeping with recent event here in Kingston about how the 1919 eclipse changed our understanding of space, time, and gravity. Hopefully the previous eclipse changed your understanding of space. But without further ado, I'll hand you off to Larry. Thank you all so much, and I'll see you upstairs in the observatory.
Great, thank you. And thanks everyone for coming out. It's kind of fun tonight to say, so how many people have seen a total eclipse of the sun? Yay, that's great. Yeah, here we go. Yeah. So so we were all, I think, really fortunate to be in the path of totality, and also to have the clouds part at just the right moment. So we're all able to view this magnificent picture of the sun and see some of the prominent effects of solar activity. How many people have seen aurora in, say, the last 24 hours? Anyone get out to dark skies? So I was out actually in South Frontenac. Unfortunately, I didn't take any pictures, but there's this beautiful shot from London, Ontario, but you can find now hundreds, thousands of pictures online from this massive storm on the sun, again, telling us something about the magnetic activity of the sun, and producing this magnificent display of northern lights. And I don't think we're going to be lucky tonight, but perhaps as we hit solar maximum, we'll have a few more storms that will produce beautiful northern lights without disrupting our satellite communication system. But that's not what I'm going to talk about today, but I am talking about the eclipse of 1919 and the sun. So I think it is relevant to the talk. Solar eclipses have, of course, been part of the human experience now for thousands of years. Humans have witnessed thousands of eclipses. They've had a great impact on our culture, religion, art, literature, and most importantly for today's talk, physics. And I think if you were to ask a physicist what was the most important eclipse in terms of its effect on our understanding of the science of physics and our understanding of space and time, certainly, then they would point to this very famous eclipse in 1919, May 29th, when the eminent British astronomer Sir Arthur Eddington mounted actually two expeditions, one to the west coast of Africa and the other to the east coast of Brazil, to measure not the eclipse itself, not to take pictures of the eclipse, but to take pictures of stars very close to the limb of the sun and to measure the deflection and the position of those stars and compare it with where the stars would be if the sun wasn't there. And what they were trying to do was see how much the gravitational field of the sun would deflect the positions of those stars, the starlight as it traveled from the star to our telescopes, and settle a debate really between what the nature of gravity was between the view of the time, which was the view that Isaac Newton had presented in his famous work, or that of the newly published Theory of General Relativity by Albert Einstein. And so that's the story of today's talk. I'd like to give you a flavor of the science that went into that eclipse experiment, how that experiment went, and then what some of the implications are and how that has really shaped much of astrophysics since that time. So that's getting a little bit ahead of the story. Our story really begins in the late 1500s with a famous experiment, I'll put that in quotes, by Galileo, in which he drops two objects off the Leaning Tower of Pisa to see if the heavier object falls faster than the lighter one. The general view at the time, the Aristotelian view, was that heavy objects fall faster if it's twice as heavy, twice as massive, then it should fall twice as fast. So that was the way Aristotle had viewed things. And what Galileo showed was that objects fall at the same rate regardless of their mass. Now, it's almost certainly not true that Galileo himself was performing this experiment. And in fact, such experiments had been performed before Galileo. But I think what Galileo really had was the thinking, the thought experiments behind this idea. And he was able to reason that objects should fall at the same rate regardless of their mass, not necessarily by doing the experiments, but by thinking about how gravity works and working it through that way. And so we attribute this idea of objects falling at the same rate regardless of their mass to Galileo. And if you've been to a science center, you know that there's a demonstration that they like to do in which you take an evacuated chamber and you drop a feather and a bowling ball. And if you have a good enough vacuum, then they both fall at the same rate. And so again, regardless of what the mass of the object is, everything falls at the same rate in a gravitational field. Well, we then turn to another sort of famous lore of physics, Isaac Newton sitting under the apple tree, contemplating how it is that the moon goes around the Earth, and an apple conks him on the head, and he has this great insight that actually the phenomena, the thing that is causing the apple to fall to the ground is the same as what is causing the moon to go around the Earth, that is the gravitational force of the Earth on the moon or on the apple. Again, this is almost certainly not a true story. In fact, I think it was Newton himself who liked to promote this as a kind of a legend of how he came up with this idea. But it nicely illustrates an idea that Newton had, a unifying idea, a unifying principle, which is something that physicists often look at, that there is a commonality in what causes the apple to fall to the ground, again, the gravitational pull of the Earth on the apple, and what causes the moon to go around the Earth, the gravitational pull of the Earth on the moon, which keeps it moving in this circular path. Just a little bit about Newton's theory of gravity. So he didn't just have this idea, this great insight, but he also wrote down the mathematical equations. And fortunately, he had developed the mathematical method of calculus, which enabled him to write down these equations. So he did the math and then did the physics all in one. Newton's theory of gravity said that, in fact, every object in the universe tugs on every other object in the universe, that the force depends on the mass of the object. So we're pulled toward the Earth because that's the most massive thing close by. And that force also decreases with distance. So the further away an object is, the weaker that gravitational tugging is, according to Newton's theory of gravity. To get some insight into how Newton came up with this, there's this famous picture from his Principia paper, this famous document that he produced about physics, in which he has this, again, a thought experiment. And so he imagines that you take a bowling ball, say at some high place, and you drop it, it falls to the ground. Now you take the bowling ball and you launch it with some horizontal velocity. So it goes a little way, but it falls to the ground. Then you launch it with more of a horizontal velocity, it goes a little bit further. So that's, I'm sorry, this pointer doesn't quite work there, but you can see those different paths that the bowling ball takes. And so it launches a bit further and goes around, and eventually you launch it with just the right speed. And that bowling ball is going to go and make a circular trajectory around the Earth. And that's the way he was able to reason the connection between the apple falling to the ground and the moon going around the Earth. He was able to sort of link them together that the moon has just the right velocity in the horizontal direction, that it keeps missing the Earth as it tries to fall towards the Earth's center. That was Newton's famous bowling ball. We kind of put these together in a first year physics demonstration, which used to be called the monkey and the hunter demonstration. I think now it's probably called the monkey and the zookeeper demonstration. And the idea is that a zookeeper wants to send bananas to a monkey. And the setup of the experiment is that the monkey is suspended far away from where the zookeeper is. And you're going to release the monkey from its suspension point at the same instant that your banana cannon fires bananas toward the monkey. And so the trick then is that you aim the banana cannon to where the monkey is suspended. You release the banana and the monkey at exactly the same time. The banana's falling in the gravitational field. The monkey's falling in the gravitational field. And so the banana and the monkey fall at the same rate, because gravity doesn't care how massive you are. And the banana hits the monkey at just the right point. And so that's one of these demonstrations that we like to do in first year physics, which illustrates both Galileo's idea that objects fall at the same rate in a gravitational field, and Newton's idea of how gravity works itself. So I'm going to jump ahead now, so we've done a little bit of historical background for this, to 1905, known as the miraculous year of Albert Einstein. It was such an amazing achievement in this 1 year of what Einstein did that in 2005, we had a worldwide celebration of physics. 100-year celebration of Einstein's achievements in this 1 year. These achievements are not all related to today's talk, but it's so wonderful. We just can't help talking about it because it's just truly remarkable what was published in that single year of physics. So the first paper in this 1905 year was called On the Heuristic Viewpoint Concerning the Production and Transformation of Light. But we know this as the photoelectric effect. It really helped usher in the quantum age. It led to CCD technology. So every time you take a picture with a CCD camera, you're using something like the photoelectric effect. And it was actually the thing that Einstein, that was noted, given the most notability in Einstein's Nobel Prize, in which he won. The second paper was on the motion of small particles suspended in a stationary liquid as required by the molecular kinetic theory of heat. So that's a mouthful, but it's known mainly as Brownian motion. And it's basically the idea that a small particle takes a jiggling random walk when it's sitting in some liquid solution. And so this helped establish the atomic nature of matter. The third paper, and that's the one most relevant to today's discussion, and I think the true masterpiece of these four incredible papers, is called On the Electrodynamics of Moving Bodies, and this was the special theory of relativity. In this paper, Einstein begins with the hypothesis that nothing can travel faster than the speed of light, and that the speed of light is independent of how fast the thing that's moving, that emitted the light, is. That is, if I'm firing this laser and I'm moving at some speed, the light doesn't go at my speed plus the speed of light, it just goes at the speed of light. And that little fact there, which is a lot to wrap your head around, actually leads to this whole theory of special relativity, which changed our notion of space and time and allowed us to understand things like how electromagnetic waves work. Something called Maxwell's theory of electromagnetism. And then the final paper was, does the inertia of a body depend on its energy content? But we know this more colloquially as the E equals mc squared paper. And this was really an add-on, an extension of the moving bodies paper, the special relativity paper. And that helped us think about how we can unlock the tremendous amount of energy in the rest mass of an object. So that paper helped usher in the nuclear age. So there's a problem, though. At this time, our theory of gravity was the theory of Newton. But Newton's theory of gravity is completely inconsistent with special relativity. So 1905, Einstein comes up with this theory of special relativity. It says nothing can travel faster than the speed of light. But then you think about what Newton's theory of gravity says. It says that according to Newton's theory, the Earth orbits the sun because the sun exerts a gravitational pull on the Earth toward it. That pull is what we call an action at a distance. It happens instantaneously in Newton's theory. And it happens by some mysterious phenomena that we're being tugged towards something that's far away. So we're being tugged toward the sun because of some mysterious force due to an object that's far away from us. And so if you imagine taking the sun and shaking it, moving it around, in Newton's theory of gravity, instantaneously, we know the position of the sun we're moving, and we would have to respond to that. So it's an instantaneous effect in Newton's theory. But Einstein's theory tells us that nothing can travel faster than the speed of light. And so if we shake the sun, the information that the sun has somehow moved its position is going to take a certain finite amount of time, about 7 or 8 minutes. That information has to take some time to reach us. And so there's this inconsistency between special relativity and Newtonian gravity. And in 1905, Einstein wasn't resting on his laurels from those 4 amazing papers. He realized that he had to resolve this inconsistency. And so that's what took him toward the theory of general relativity, a theory of gravity. Otherwise, you have this theory of Newtonian gravity and special relativity, and the two just don't work together at all. So in 1911, Einstein's sort of thinking about how to fit gravity in with this theory of relativity, and he realizes that light itself should behave just like the bananas from our banana cannon. They should behave just like the cannonballs in Newton's experiment, that light itself should follow a curved trajectory due to the gravitational field in which it's being released in. And so if I shine this laser across the room, well, that laser beam, if I go 10 meters, that laser beam takes about 30 billionths of a second to cross the room. And it falls about 5 femtometers, or about a billionth the width of a human hair. So this is actually following a curved path, but that change is so tiny that we'll never detect it. But indeed, the light is following a curved path. What Einstein realized, perhaps talking to some of his astronomer friends of the day, is that even though we'll never measure the curvature of the path of this light beam as it crosses the room, if we look at the star as it goes past the limb of the sun, then that change in position as the light tries to fall into the sun due to the gravitational field of the sun, then that change in position is actually going to be something that an astronomer can measure. And so you have to think about this a little bit. Well, you're never going to see a star right at the limb of the sun because the sun is too bright, except during a solar eclipse, because during a solar eclipse, you can see stars right up to the limb of the sun, as long as the corona isn't interfering too much. But outside, beyond the corona, you can see the stars if you take a good photographic image of the patch of sky right around the eclipse. And so what you do is you take an image during the eclipse, you measure the positions of all of those stars, and then you take a patch of the same sky 6 months later when that patch is up in the sky in the middle of the night. You compare the two, and by comparing the two, you should be able to see the fact that the light traveling around the limb of the sun was actually following a curved path, and that may tell you something about the nature of gravity. And so that's the idea of the eclipse experiment that Einstein and others, Eddington and so forth, had as he was thinking about gravity and Newtonian physics. Now, how many people here do sort of amateur astronomy? Anyone doing? A few people, perhaps. That deflection amount is about 1 arc second. And so even if you don't do much astronomy, an arc second doesn't mean anything to you. but that's about 1/2000th the angular size of the moon. So that's a very small deflection, but it is an amount that you can measure by taking images with photographic plates, which is what they had 100 years ago, or CCD images, which is what you would do today. And so you should be able to see the shifting of the positions of the stars due to the gravitational field of the sun if you compare the image during an eclipse, which is what this image is, and you compare it with the same patch of sky 6 months later. And so that's again, the idea of the eclipse experiment. Now, I think it's worth measuring. So this seems like a very small effect. So is this really important? Einstein is a really tiny effect. Maybe it's just tweaking Newton's theory a little bit. But I think it's worth pointing out that Einstein's theory is not simply a modification or an extension of Newton's theory, but a radically new picture of space and time. So even though the effect is small, the way of thinking about space and time is completely different. Einstein's insight really goes back to this idea from Galileo that all objects fall at the same rate in the gravitational field. He reasoned that all objects follow the same path in space, and therefore its gravity is a property of space itself rather than some mysterious force of a distant object tugging on it. And so that gets to this picture that I started the talk with, which is that if you imagine a massive object like the Earth or the sun, what it's doing is it's warping space. And the reason objects follow the trajectory that they do is they're going as straight as they possibly can in this curved space. And since space is curved, and that's an intrinsic property of space, everything, whether you are a feather or a planet or an astronaut, you're always going to follow that same trajectory because that's just the way space is. Space tells you how to move, regardless of how massive you are. So you could put a feather at the same orbital position as the Earth, and it's going to follow the same trajectory as the Earth. So Einstein's result for the bending of light in 1911 can actually be obtained from Newton's theory itself. And so this is a little bit of a worry. Newton himself pondered whether light would be bent by a gravitational force. And so back in 1704, in Newton's treatise on optics, he writes, "Do not bodies act upon light at a distance, and by their action bend its rays, and is its action not strongest at the least distance?" He's saying that light should behave just like particles and be bent by the gravitational field. And so this would seem to be a problem. With this experiment, because if Newton predicts this and Einstein predicts this, then how can we tell which theory is the correct theory? Right? If both theories are making this prediction that light should be bent by gravity, in Newton's case, the gravitational force, in Einstein's case, the curvature of space, then we don't have much of a way of distinguishing between the two theories. Well, it turns out that that 1911 paper was really an incomplete theory. Einstein hadn't finished developing his theory of relativity just yet. It explained the motion of light in curved space, but it didn't explain how space itself was curved. And so he still had some work to do. Wasn't quite done yet. That piece of the puzzle actually came in 1915 and 1916 in a pair of papers on special and general relativity. And those, I think, are truly two of the most remarkable papers in all of physics. Just breathtaking in what they showed us. So we can't go through the mathematics of that. That takes about a semester of a fourth year with a lot of math, but it's fun to do. So I encourage anybody who's thinking about going into physics, take such a course. But we can get an idea of how this works by thinking about the following thought experiment. So all along, we've been thinking about thought experiments. So here's a thought experiment. Imagine we lived on a world that was much like Venus, totally enshrouded in clouds where we couldn't possibly see out to see the stars. What could we detect on Earth that would tell us that there's an object, the moon in this case, that's going around the Earth? And in fact, we could also figure out that the sun also moves relative to the Earth. What could you see on Earth that would tell you what's going on outside of the Earth, just even if we're shrouded in clouds. Yeah. So you're very close. In fact, I think that's a good answer, but there's something even more obvious. Tides, exactly. So you're exactly right that the gravitational force of the moon is going to affect the clouds. But the thing that we're all familiar with is the idea of tides. And so you can think of these arrows show you the gravitational force of the moon acting on the Earth. And it's sort of the average force at the center of the Earth, but then it's a little bit stronger on the side closest to the moon, a little weaker on the other side. It's pointing at an angle from the sides. And if we subtract off the average force from the center, then what we're left with is the fact that on one side, we're tugged a little more toward the moon. On the other side, it's being tugged a little bit away from the center of the Earth, rather. And at the sides, it's being tugged toward the center of the Earth. And so again, you want to think of taking that arrow in the middle, subtracting it from all the other arrows, and what you're left with is what we call a tidal field, because it's the tides. And that's what gives us that little bit of bulge in the oceans on two sides of the Earth, and a decrease in the water on the two sides, sort of perpendicular to the pointing toward the moon. So Einstein then, thinking about the tides, thinking about the equations, and learning a bit of mathematics, comes up with this theory of general relativity. And the basic idea of the theory is encapsulated into an equation, which I just write schematically, that space-time curvature, or tides, is equal to a constant. We'll call it Newton's constant. So we still think about Newton in all of this, times something having to do with the mass or the density of matter. And so he publishes this in about 1915 or so. And almost immediately, this is quite remarkable, Karl Schwarzschild, while serving in the German army, writes down one of the first exact solutions to Einstein's equations, which describe the space curvature outside of spherical massive bodies. And to this very day, it's the starting point for understanding things like black holes and the gravitational field outside the sun. And so with Schwarzschild's solution, one predicts that light from a distant star is bent, just as Newton had said, Einstein had said in 1911, but by an amount exactly twice the earlier prediction. And so originally Einstein had this prediction, and I would have said, well, Newton, Einstein, they both predicted the same thing. But once he had the complete theory and Schwarzschild's solutions, he actually realized that his theory predicted double the bending of the light that was originally predicted. So instead of 0.87 arc seconds, it's 1.75 arc seconds of bending of the light. That's good for astronomers because it's a little bit of a bigger bend, but it gives us a clear way of distinguishing between Einstein's theory and Newton's theory. So in fact, the first attempts to measure the deflection of light by the sun were made by three different groups, one from Argentina, one from the US, and one from Germany in 1914, before the new theory had been developed. The images that the US and Argentinian group obtained were too poor, and so they weren't able to measure the deflection. And the German group wasn't able to go because, well, they were in the middle of this world war. And this eclipse was actually occurring in the Crimea. And so you can see already how geopolitical events are affecting astronomy. But perhaps this is fortunate from the point of view of physics, because Einstein didn't have the complete theory yet. And so perhaps the interpretation would have been murkier had they had good images from that experiment. So now we jump ahead to 1919. There's an eclipse which crosses the Atlantic Ocean from Sobral, Brazil, on the east coast of Brazil, moving across to the west coast of Africa. And so with Arthur Eddington, with the help of Frank Dyson and other astronomers from Cambridge, set up 2 expeditions to go take images of this eclipse in 1919 and see if they could measure the deflection. So already Einstein's theory was a few years old. People had started to understand the implications of that theory and were ready to test whether it would be Einstein or Newton that would win out. So here's an image of the 1919 eclipse. You can see that prominent, the prominence at the upper right part. So think about what you saw in the eclipse back on April 8th. Quite fortunately, this eclipse was in a very crowded part of the sky, so there were lots of stars around. It was close to the Hades star cluster, and so there were lots of good targets for measuring the deflection of light. Here's the telescope from Sobral, Brazil. Here's an image of the townspeople gathering to view the eclipse. And here's a picture that I took at Breakwater Park in Kingston with canoes and so forth out watching, waiting for our eclipse. There's an interesting account. So Eddington wrote about the eclipse in his diary, and that was that appears actually in a biography of Sir Arthur Eddington by Oliver Douglas. That's a bit of Queen's connection with this story, so it's nice to recount this. So Douglas was actually a former student of Eddington's and wrote one of the main biographies of Eddington. And so she actually simply relates what Eddington wrote in his diary about the eclipse. I think it's kind of fun to read this. On May 29th, a tremendous rainstorm came on. So think about how we were feeling on April 8th with the clouds coming in and out and the weather looking grim. So he woke up and it was just pouring rain. The rain stopped about noon, and about 1:30, the partial phase was well advanced, and we began to get a glimpse of the sun. We had to carry out our program of photographs in faith, as they were too busy taking pictures to just sit there and admire what was going on. I did not see the eclipse being too busy, except for a quick glance to make sure that it had begun, and another halfway through to see how much cloud there was. We took 16 photographs. They were all good of the sun, showing a remarkable prominence, but the cloud has interfered with the star images. The last 6 photographs showed a few images, which I hope would give us what we would need. So it was a little touch and go as whether they would actually be successful. And then a few days later, we developed the photographs, 2 each night for 6 nights after the eclipse. So no instantaneous, oh, let's just scroll through my cell phone and see what these pictures look like. I spent the whole day measuring the images of the stars. The cloudy weather upset my plans, and I had to treat the measures in a different way from what I intended. Starting to worry a little bit about some of how he's doing the analysis. Consequently, I've not been able to make any preliminary announcement, but one plate I measured gave a result agreeing with Einstein. So this is all very interesting to see how this was done and how he was taking these measurements and trying to figure out which of the photographic plates would have a good enough image to make the measurement. Here's the data from the Eddington's paper. And so in this plot, we're actually showing how much the deflection is of each star as a function of their distance from the limb of the sun itself. So the further away the star's path takes it relative to the limb, the less the deflection is. And so that's what they're doing. And the best fit line is the one at the top. Einstein's 1916 prediction is that line in the middle, and Newton's prediction is the dotted line at the bottom. And the data seem to be mostly consistent with the prediction of Einstein's theory. And so this was taken to be the first experimental confirmation of Einstein's theory of general relativity. This actually was one of the things that made Einstein famous. So I think he was well known among physicists at the time. But this triumph of Einstein's theory over Newton's theory really captured the imagination of the popular press. And this is a famous article from the New York Times after the results were announced at a meeting of the Royal Society. So this is already in November 1919. Lights all askew in the heavens. Men of science more or less agog over results of eclipse observations. They couldn't find one headline that they liked, so they wrote 6 headlines. Einstein's theory triumphs. Stars not where they seemed or were calculated to be, but nobody need worry. A book for 12 wise men. So Einstein was famous as saying that no more in all the world could comprehend it, said Einstein, when his daring publishers accepted his paper. So the work is pretty tough. So this is it. This was the announcement really that we had a new theory of space, time, and gravity. I think that comment about no more than 12 people could understand Einstein's theory is interesting to think about in the context of today's world. If you look on popular books on general relativity, you come up with dozens, perhaps even 100 books. Some of them really great for the sort of popular press type book. Others that are more technical. Some of these that I've used as an undergraduate, some of them that you would use in graduate school. But there's just lots of different ways to approach the subject of relativity, lots of interesting things that you can read at different levels. Perhaps one of the most famous, though, is the mathematical theory of relativity by Arthur Eddington himself. And this is considered one of the first really excellent expositions of the theory of general relativity, and in fact earned the Einstein seal of approval. He thought this was a really brilliant, extremely clear presentation of the theory itself. So I thought I'd spend the last part of the talk just telling you some of the other implications of relativity. One, as you might imagine, is that if you shine a laser beam, so I showed you earlier that the laser beam, as you can see here, is bending. It's bending by 1 femtometer, but it is bending. If I shine it upward like this, then it's actually losing energy as it climbs out of the gravitational field of the Earth. And so it's shifted a little more toward the red. And so a blue light will be shifted to a red light as it travels away from a massive object. This has some interesting implications. For example, if you were to take 2 clocks, 2 atomic clocks, and send them one to the top and the other to the bottom of the CN tower, let them spend 100 years at the top and bottom of the CN tower, then they would differ, and bring them back together again and compare them, they would differ by about 150 microseconds. So the clock at the top of the CN tower would be ahead of the one at the bottom of the CN tower by 150 microseconds. This experiment was actually done, not this particular experiment, but by 2 people who flew atomic clocks on jumbo jets around the Earth and then compared them. And you're actually testing the theory of relativity and how it affects time itself. And if you've seen Interstellar, then there are these sorts of effects at much stronger level as you're near a black hole. And that movie, in fact, had Kip Thorne as one of its consultants. In fact, it was his idea. The whole idea of the movie really is due to Kip Thorne. And so this is a serious relativity expert behind that movie. But this idea that clocks are affected by a gravitational field and by their motion is something that affects the clocks that are ticking on GPS satellites. And so if you want the resolution that we get with our GPS satellites in trying to identify where we are on the Earth, you need to make corrections both to the general and special theory of relativity. So there are other effects. Einstein's observation is really the first example of what we call gravitational lensing, the bending of light by massive objects. In this animation, imagine a star, which is shown as that kind of light blue star is passing behind a massive object. As it does, the light from that star is bent by that massive object, just as the light is bent by the sun. But in this case, if that object is very compact, the effect is much stronger. And so what you see is not the blue dot, but in fact, what you see is that white dot. And so in fact, you get what's called an Einstein ring. As the light is bent and going around this massive object, it can form momentarily a ring, and in fact, two bright images. And so you can get multiple images, and you can get rings and all sorts of interesting effects. And so this is called gravitational lensing, and it's now a tool that we use in astrophysics to measure the mass of different objects. So imagine a distant galaxy whose light is going to be bent by some intervening galaxy or cluster of galaxies. We might see multiple images of that background galaxy. We might see that image distorted. We might, in fact, see some of those images brighter than they would be if the intervening galaxy wasn't there. And so this is the famous Einstein cross, in which you get 4 images of a background galaxy. So those are 4 different images of one object as they're bent by some intermediate object. Here's a beautiful picture from James Webb Deep Field. And notice all of these arcs, and those are background galaxies whose light is being distorted by the intervening lens. And so again, exactly the same physics that Eddington and Einstein had thought about over 100 years ago. Now we're seeing the light from distant galaxies being stretched and bent and brightened and dimmed in all sorts of interesting ways. And so here's, again, a close-up of one of these James Webb pictures. And you can see all of the interesting arcs. And astronomers are able to take all of these different images and study them and learn something about the mass of the intervening lens and about things like dark matter and so forth. So this is one of the real important tools now in observational astronomy. Other interesting features of Einstein's theory of relativity. This is a simulation of 2 black holes merging together. And so we don't actually see this, but what we're going to see is the effect of the gravitational field being shaken and stirred as these 2 black holes merge together. And so remember my thought experiment early on when I said, suppose someone came and shook the position of the sun. Seemed like kind of a silly experiment, but that really is what's happening here. You have 2 objects that are stirring up space-time, and they're producing waves, and those waves then travel at the speed of light, and they travel from those 2 merging black holes to detectors that we have here on Earth, namely the LIGO detector, and produce minuscule changes in those long arms of the LIGO experiment, but actually give us the smoking gun of the fact that somewhere in the distant universe, 2 huge black holes merge together. And so we now have, I think this is one of the most remarkable things in the last couple of decades, last decade really, of astrophysics, a picture of masses in the stellar graveyard. And so all of these dots in this image correspond to 2 black holes merging together, forming some larger black holes. And we're starting to get a picture of what these compact objects are in the early universe. And then finally, along the line of black holes, again, another, I keep saying truly remarkable, these are truly remarkable. This is an image of the black hole itself at the center of a giant elliptical galaxy, M87. And so here's the galaxy itself. This is 5,000 light years across, so it's much bigger than our own galaxy. We zoom in by a factor of 10 million using the magic of radio astronomy and the fact that you can use radio telescopes scattered across the Earth and combine them in clever ways to produce a telescope basically the size of the Earth. and get the resolution that allows you to image that central black hole. And so from this galactic size object, we're able to image down to something basically the size of the orbit of Pluto. We're down to a solar system size inside this big galaxy. This image then is telling us something about all the matter swirling around this black hole, producing radiation, and providing a wealth of information about the physics inside these most massive black holes that we have in the universe. So let me close then with this beautiful picture of an Einstein ring. So again, if you have a background object directly behind a massive object, then the light from that object is going to be spread out into a ring. So that blue circle, almost complete circle, is one object whose image has been distorted. And I'll leave you with a limerick from Sir Arthur Eddington, talking about his own experiment that I thought was quite clever. "Oh, leave the wise our measures to collate. One thing at least is certain, light has weight. One thing is certain, and the rest debate. Light rays, when near the sun, do not go straight." And I'll leave it there. Thank you.